Hey, hello there. So today's Leetcode challenge question, it's remove k digits. We have a non-negative integer number represented as a string. We want to remove k digits from the number, so the new number is as small as possible. So a couple of notes here. The maximum length for this number string is going to be less than this, and it's guaranteed we can move at least the k digits from the number. The second thing is the number shouldn't contain any leading zero. So let's look at some examples. 1432, 219. We can remove 3 digits from it, so we remove 432. So the end result is 1219. And the second example is 10,200. We can remove 1 digit. We remove the first one, and we end up with a number that has a leading zero, so we get rid of the leading zero, which leads us to 200. So that's the smallest we can do by removing 1 digit. The third example is 10. We can remove 2 digits, essentially reduce this to empty string. So whenever we have an empty string, we should actually return 0. So that the code should be able to handle that case. It should probably just be some logic in the return statements. And if you ask me if just directly thinking about remove k digits is going to be a little bit difficult, but we do see that a special case, really degraded version of remove k digits is going to be remove 1 digit. And we can actually, if we can code the special case remove 1 digit, we can just throw that into a loop, run that loop for k times, and we essentially effectively getting a remove k digits algorithm by calling remove 1 digit k times. So it's worthwhile to think about how we're gonna do this remove 1 digit. So let's look at some examples. The one from the question, definitely we want to remove the first one, and if we have some extreme case 1 2 3 4 5, we should return the 5. If we have the other kind of extreme 5 4 3 2 1, we should return the 5. If it's some random pattern one, we should return the 5. We should get rid of the 5 if we're talking about getting rid of 1 digit. So notice that the element that the digit that being removed, it's the top of the hill for the leftmost kind of a peak. So it's the leftmost peak value. The reason being that if we remove the elements that's prior to the peak, after removal we should shift everything from its right towards left by 1, so we end up with a peak that's even higher. So that's why we should identify, if we do this remove 1 element at 1 digit, we should look for the leftmost peak and just remove the peak value. So that's pretty much remove 1 digit. So let's code this up very quickly. So initially we are looking at, we're going to compare the value with its prior. So let's look at the 3 and 5. If the prior is less than or equal to, it could be the case that if we are equal to, that's also we can remove either one is fine. So just for the code to be a little bit nicer, we can remove the latter one. So if the previous value is less than or equal to the current value, we should keep looking towards right. Whenever we see the first decreasing, then we know that we get to the peak. So that's so we start with L equal to 1, while we're still less than the total length of the number, and we are still in the upward trend. So it's -1 and the L. We should increment the L's value, and in the end we should just return. The first time that this condition gonna break is when L minus 1 it's larger than L, which means that L minus 1's location is the peak. So we should pretty much just get rid of that digit. So it's a number upon until the L minus 1, just immediately before that, and concatenating with the digits from L and on. So that's remove one digit. So in the body of this remove k digits, we're just gonna, in a loop, call this function k times. And we end up with a working solution for this problem, pretty much. Some of our housekeeping work is to remove the leading zeros. So we're starting from the leftmost position and scan towards the right to find the first non-zero element. So that's pretty much it. We just return the number from that position and on if it's not empty. Otherwise, we would return a 0. So yeah, so that's the code for code up remove one digit and use that for k times. So it's working. But we do see the problem with this is that we're scanning from left to right in each iteration, in each time that we call this, and it's redundant because once we remove the peak, the new peak, the new leftmost peak is going to be the immediate value that's prior to the one that we removed, and then we just in the second iteration, when we call this function call remove one digits, we're gonna pretty much just do this this while loop until this previous peak, the elements that's one before the previous peak, doing nothing, and then resume from there. So the way that we can reduce this is to reduce this time complexity is pretty much use a stack to keep track of the previous values, so that if we remove one value, if actually you remove the leftmost peak, we just pop out the value from this stack, then the new top element is going to be the new leftmost hill. So we just do this leftmost hill scan continuously. Once we pop k elements from the stack, we're going to end up with the numbers that we want. So that's pretty much an improvement for this. So let's code that up. Yeah, so as I mentioned, if we code this remove one digit and analyze the redundancy when we actually call it k times, we find the linear scan from left to the peak, it's redundant, because when we remove one of the peak, leftmost peak, the elements that's one prior to that is going to be the new peak. So if we use a stack, when we pop out the top element, the new top, it's going to be the new leftmost peak value. So that's pretty much the reason that we can use a stack for this purpose. So for a digit in this number, we should just append this to the stack, and then it's the peak popping. So when we see a decreasing trend there, then we could pop the hill value, and if the new hill is still higher than the downward value after that, then we should also pop this new peak value. And so that's pretty much just a while loop. So while we have something on the stack, and k is we haven't popped out k values yet, and the peak, the current peak, is actually higher than the value that we are looking at, the right hand side value we are looking at. We should do two things. We should decrement the k because we actually popping out one value, and then is the actual pop. So that's pretty much the for loop to use the stack. And I guess one more thing we need to handle is if we haven't popped out enough values, that's equivalent to the case when we have a sort of after popping some partially pop off some digits, so we end up with an strictly increasing sequence of digits. then whatever the remainder k is, we should just grab the digits from the beginning towards the k, towards the, just exclude the rightmost k values. So if the k is not 0, we should the stack we should slice this to be, so it's until the left rightmost k values. So that's pretty much it. And then just need to do a little bit variable renaming. So let's just change this to num actually. Nope. Yeah, I will just do a rename so that the code should work. Yep. Nope. Oh, it's a stack of characters, so now we need to actually join them. So, okay. Oh, I can do this. So that is not just a reassignment. It's stitch up the string there, and then do the leading 0 slicing. So we can still reuse this code from the previous simple solution. Okay, yeah, it's working as well. So this gives us the linear time algorithm. It's strictly linear time, but the remove one digit called out k times is going to be n multiplied by k, and this is using stack is going to be order of n in time. It's just one loop, and yeah, that's pretty much it. The linear time and linear space. The stack can go up to, if it's in the continuously increasing case, it will pretty much just store everything in there. Oh, it's gonna store everything in there. There's no breaking here. No matter what kind of pattern there, the stack is gonna be the same size as the input string. So yeah, linear time, linear space. And we arrived here by looking at the special case, reduce the version, remove one digit, and analyzing by what kind of redundancy we have by repeatedly utilize this remove one digit to solve the problem. The redundancy is in there, from left to right scan. It has to restart from the leftmost position every time. Using the stack, it's effectively restarting from the new peak every time. So yeah, so that's pretty much the question for today.